Okay, so this is going to be the fourth and final exercise on this worksheet, exercises on area of planar regions. This worksheet is an introduction to area using vertical slicing. There's going to be another worksheet following, which is area using horizontal slicing, so we're not quite done area. We're going to scroll down here to the fourth question. And the fourth question is asking us to find the region bounded by y is equal to ln x, its tangent line at x equals 1, and the line y is equal to 1. So we have an extra preparatory step here, and that is to find the equation of one of the missing boundary curves, the tangent line to the logarithm at x equals 1. So if we know that y is ln x, then the derivative is 1 over x, and if we look at x equals 1, we can evaluate both of these things. So y of 1 is ln of 1, which is 0, and y prime of 1 is 1 over 1, which is 1. So the tangent line we can find by using the slope-intersect form of the line, y is equal to mx plus b. We're going to use m, the slope value, as the value of the derivative, so 1, and the known point, the point of tangency, is the point x equals 1, y equals 0. So we'll take that into the equation, so y is equal to 1x plus b. We'll substitute in the known point, so 1, note the y is 0. 0 is equal to 1 times 1 plus b, or b is equal to minus 1. So the equation of our missing boundary curve is y is equal to x minus 1, the tangent line to the logarithm at x equals 1. So let's go ahead and draw the region so we can get an idea of how to set up the integral or integrals that are necessary. So here, if we put in our logarithm curve, we know that it's going to cross the axis at 1. So this is y is equal to ln x. We've just found the equation of the tangent line is, here y is x minus 1, and the missing boundary curve, I'm going to adjust my scale a little bit so that the diagram is easier to read, and this is our line y is equal to 1. So the region that we're asked to find the area of is bounded by these three curves, so almost triangular, a bit of a curved base here. And if we're paying attention to the region, we're going to notice that something happens halfway or part of the way along, and that is a shift in boundary curves. So what I mean by that is, if we imagine drawing our rectangles for Riemann sums in the left-hand part of the region, then those rectangles are going to go from the bottom curve, which is the logarithm, to the top curve, which is y is equal to x minus 1. But if we were to draw rectangles for Riemann sums over in the right-hand side, then the bottom curve is still the logarithm, but the top now is y is equal to 1. So at this point here, through the region, the boundaries change. So to evaluate the area, we're going to evaluate the area of region 1 and the area of region 2, but to do that we need to find these points of intersection. So let's call them P and Q. And to find point P, we need to do the intersection of the line y is equal to 1 with the line x is equal, y is equal to x minus 1. So that is going to tell me that x is equal to 2. And for point Q, it is the intersection of y is equal to 1 and of the logarithm. Using the exponential form of that, x is equal to e. I was going to write e is equal to x, same thing. So x is equal to e. So the area that we want can be found by summing the area of those two regions. And that means that we can set up two integrals and add them together. So the integral for the first region is going to be from 1 to 2, of the bottom curve is the logarithm. The top we want first, so x minus 1 minus the logarithm. And then the integral for the second region is going to be the region from 2 to e. The integral from 2 to e of the top curve now is just 1 minus, and again, the logarithm. So we're going to use the following fact that can be shown using IBP, integration by parts, and in fact we did so in class, but if you don't remember this fact, then you should probably go through the exercise of using integration by parts to determine an antiderivative, or the family of antiderivatives for the logarithm x ln x minus x plus c is the general antiderivative of the logarithm. So we're going to use that here so that we can evaluate our two integrals using FTC part 2. Integral of x, 1/2 x squared, antiderivative of x minus x, minus, and we're going to use what we just wrote up top, x ln x minus x. That first integral is evaluated from 1 to 2, plus the second integral antiderivative is x, and again minus x ln x minus x, and this will go from 2 to e. Let's simplify a little bit within the brackets, and if we look, these x's are going to cancel out. So the first bracket will give me 1/2 x squared minus x ln x, evaluated from 1 to 2, plus, and in the second bracket, if we distribute this negative sign, negative negative will give me plus x. So I'm going to get 2x minus x ln x, and that will be evaluated from 2 to e. First integral then, so 1/2 of 2 squared is 4, minus 2 ln 2, evaluating at the top, minus the bottom, so the bottom is 1/2 of 1 squared, so that's just 1, minus 1 times ln of 1. Ln of 1 is a nice value. It is what we used above. It is 0, so that term is going to go away. Plus, and then on the right-hand side, we have 2 times e minus e ln e, minus, and 2 times 2, I'll open a bracket here, is 4 minus 2 ln 2. Ln e is also a value that we've used up above, a famous value that is just 1. So let's simplify again. So 4 divided by 2 is 2, minus 2 ln 2 minus 1/2, plus 2e minus e times 1, so just minus e, minus 4 minus minus plus 2 ln 2. Those values will cancel. And so I have all I have left to do then is to collect my like terms. So if we go for the e values, 2e minus e is just going to be e. And then 2 minus 1/2 minus 4 are the numerical values that are left. And so 2 minus 4 is minus 2, so minus 2 minus 1/2 is going to be minus 5 over 2. So e minus 5 over 2 units squared is the area of the region.